Alright, this is for Project 3 for Fundamentals of Aerospace, or Aerodynamics with Ozbay. I'm doing part E, um, which is determine the pressure gradient using the Fluent results with theory. So first we're going to find the pressure gradient using Fluent. So we've already got our velocity profiles and stuff here, and I went ahead and already went into the plots here and made a point for our end points and midpoint. We decided to make our pipe 450 millimeters long. So our midpoint's at 225 millimeters, and the height is 3 millimeters. So we're going to go down here to surface integrals, double click that, and then you click area weighted average, pressure, static pressure, and then if we just do the endpoint and the midpoint, click compute, and that's going to give us these values here. Now, in order to find the actual pressure gradient, what we're going to do is we're going to take the output, subtract the input, and divide by the distance between them. And that'll give us the pressure gradient. So the distance between them is half of the length of the pipe, so that's 225 millimeters. So if we take these two values, negative 0.0832 minus 23.5896, and you get negative 23.6728, and then divide that by 0.225. That's going to give us negative 105.21. So that's the pressure gradient we got from Fluent. And now I can show you the theory behind this. So if we just go with our theoretical calcs, we're going to start with the Navier-Stokes equation, and we make some assumptions here. We know the flow is steady. We know it's horizontal. It's 2D. We know it's laminar and fully developed. So we get our simplified Navier-Stokes equation down here, and we solve for our pressure gradient. And then solve for del squared u over del y squared, and then we integrate twice to get our velocity function here. And we're going to have two constants here, or not constants, but coefficients here that we need to find. So we're going to use our boundary layer assumptions. We know on the bottom plate y equals 0, and our velocity is given to us in the instructions, negative 2 meters per second. And then on the top plate, y is h, or 3 millimeters. And then our top velocity is 3 meters per second, positive. So we do the first one, we go ahead and sub our values into that equation that we got here, and we can go ahead and solve for C2, which is negative 2. Do the same thing again with the next values. We can put in that C2 down here as well. Solve for C1. Substitute this back into the velocity function here to get it on its own. And then we can take the conservation of mass. We know that it's steady and incompressible, so we can make this assumption here. This is from the conservation of mass. We know the volumetric flow rate right here, using this conservation of mass as well. The volumetric flow rate equation is velocity times area. So we know the area is h times, we're going to use just some unit vector here, or the unit value of 1 here. So that gives us our V average equals 1 over h, the integral of this, uy multiplied the h over here. And actually, I brought it back down over here. Okay, I see. We know that if the inlet has 5 meters per second and it has a constant area down the pipe, then the exit's got to have 5 meters per second. Um, Otherwise, like it has to, for conservation of mass, like the flow has to go somewhere, right? So it has to be coming out at the same amount of mass flow rate at the end. So we can say that the average flow rate is the same throughout the entire thing. So we're going to say it's 5 meters per second because that's given to us. These are some of our given values. And then we go in here and just sub everything back in to our the average equation here. So I multiplied the h back over, so 5h, and then equals this gnarly integral. Should we do the integral for y? Sub the h back in. Take the pressure gradient. Oh, pressure gradient out. Here's a common variable here. Take that out. Divide over here, and then again with the same thing, take it out, and then input our values, our givens, and we get negative 107.364 pascals per meter. And so we got from our fluent value earlier, negative 105. It's fairly close. It's pretty dang close. Pretty dang close. So yeah, this is basically just going over the values from Fluent, and the theory behind this is where we're taking the midpoint pressure out minus the pressure in, so the midpoint pressure minus the exit pressure over the midpoint length, the distance between them. And we get this, and we can do the error calcs between them, and it's only 2.13% error, which is pretty close. At that point, I don't think the flow is quite fully developed, so I think that's why there's a little bit of error there, because yeah, if technically it should be fully developed in order for us to get the proper flow, the gradient to be exact, because I think this calculated thing is kind of like assuming like an infinitely long pipe.